Hi everyone, my name is Yoshitomo Matsubara. In this video, I'm going to give a presentation about our work, SC2 benchmark, supervised compression for split computing. This is accepted at TMLR, Transactions on Machine Learning Research. This work was done with Ruihan Yang, Marco Lavorato, and Stefan Mann as part of my PhD program at University of California, Irvine. Okay, let's start with the background of this study, and we will briefly review supervised compression and split computing. Nowadays, computers are part of our lives in various forms such as smartphones, personal computers, drones, monitoring systems, and cloud edge servers. It is also true for the machine learning and deep learning applications. While deep learning models have been getting used in the real-world applications, accurate deep learning models still tend to be too complicated, overcomplex to be executed on mobile devices. A popular approach to this problem is fully offloading computation via wireless network from the mobile device to an edge server, where complex deep learning models are executed and return the prediction to mobile device. Note that the cost to return the prediction result from cloud or edge server to the mobile device is negligible compared to sending a sensor data, input image in this case, from the mobile device to the cloud or edge server. In resource-constrained edge computing systems, a few drawbacks of the previous approach or input compression for full offloading will be more significant. There are three main components of resource-constrained edge computing systems: mobile device, wireless communication, and cloud edge server. Mobile devices usually have limited computing resource and battery constraint, and the wireless communication has limited channel capacity and/or unstable connectivity. Cloud or edge servers have relatively powerful computing resources, such as GPU, compared to mobile devices. Thus, the processing delay at the server side is negligible. In the input compression scenario, especially when using neural compression models, the compressor requires heavy encoding cost for mobile devices while their computing capacity is very limited. Another big issue is that the compressed input data include irrelevant information to supervise tasks, since the cloud or edge server will need to reconstruct the original input data from the compressed data for a full deep learning model deployed at the cloud or edge server. In other words, input compression methods sends large data to the edge server to achieve high prediction accuracy. However, in such resource-constrained edge computing systems, it is critical to minimize both encoding cost and the size of the data to be offloaded while achieving high model accuracy. Supervised compression for split computing, shortly SC2, directly addresses the problems. Split computing literally splits computation of a deep learning model into two sections at runtime, and the first and the second sections will be executed at the mobile device and edge server respectively. Different from input compression, this approach will place a lightweight encoder on the mobile device, and which can compress the data more than the encoder of the input compression can do, while achieving higher model accuracy. This is technically possible because the compressed feature will not be used to reconstruct the original input data, but instead preserve information more focused on the target supervised tasks. As shortly mentioned in the previous slide, we define supervised compression as learning compressed representations for supervised downstream tasks. Here, we provide an illustrative example to compare a supervised compression method to a neural input compression method. Specifically, we compare bit allocation of compressed representations by a neural input compression method, factorized prior, with a supervised compression method, entropic student. Given the input images at the left column, the supervised compression method allocated more bits to the object in the images than the input compression method did. Such areas are highlighted by red color, and blue areas are where the neural input compression method allocated more bits than the supervised compression method did. Okay, now we focus on issues in the evaluation metrics used in existing studies on split computing, which we address in this work. Machine learning community is still relying on BPP, or bit per pixel, and rate distortion trade-off for assessing supervised compression approaches. However, this is a critical issue, especially for split computing, since minimizing BPP does not necessarily save the communication delay from a mobile device to an edge server. This is because even when the resulting compressed representation has large data size, the corresponding BPP can be small if the input image has more pixels as its bit per pixel. For these reasons, we use the actual data size of the compressed representation as weight term and the model accuracy as distortion for SC2 benchmark. Notice that the supervised task rate distortion trade-off still misses an important criterion: encoding cost on mobile device side. In the next slide, we will explain why it's important to consider encoding cost. As you might have noticed, it is very easy to improve the rate distortion trade-off if we design a bottleneck or splitting point at the late layers of the deep neural network model. For example, before the output layer, since the features close to the output layers are significantly smaller than the input data. However, it will result in executing most of the model inference at the weaker mobile device. In fact, some of the recent studies introduce bottlenecks or splitting point at the late layers of less than 50, which is a popular reference model for split computing studies, and show improved rate distortion trade-offs. But these approaches impose 34 to 92% of the model on weak mobile devices, and the encoder size is 60 to 170 times larger than the encoder of the entropic student, which is the state-of-the-art supervised compression method. To design more reasonable trade-offs for SC2 problems, we define and consider encoder size as part of our new trade-offs for SC2 evaluation. One simple approach is just introducing the encoder size as an additional dimension in the trade-off, which we refer to as three-way trade-off, as shown in the right figures. We also propose XRD trade-off, where we use encoder size multiplied by data size instead of data size only. This new 2D trade-off may be easier to understand than three-way trade-off in SC2 benchmark. Using the proposed metric and new trade-offs for SC2 problems, we perform comprehensive SC2 benchmark experiments. In this study, we assessed 12 baseline methods using more than 180 trained models, while existing studies assess split computing methods for one or two tasks, and many of the tasks use two small images to motivate split computing scenarios, such as 32 times 32 pixels images in CIFAR datasets. Our benchmark involves multiple target tasks with large images, specifically image classification for ImageNet dataset, object detection for COCO 2070 dataset, and semantic segmentation for Pascal VOC 2012 dataset. We provide more details in the following slides. As baselines, we consider three types of the codec-based and the neural methods: input compression, feature compression, and supervised compression. Input compression methods compress input data by their encoders and reconstruct the original input data by their decoders. We use popular and strong codec-based and neural baseline methods. Feature compression encoders compress intermediate features instead of the input image data, and their decoders reconstruct the features. For supervised compression, we consider channel reduction and bottleneck quantization, shortly CR plus BQ, which is a popular method in split computing studies, and two neural image compression-inspired methods, end-to-end compressive feature and end-to-entropic student. Here, we provide three trade-off evaluations: conventional rate distortion trade-off, XRD trade-off, and three-way trade-off. For image classification, we used ResNet50 as a reference model. For object detection and semantic segmentation, we used faster RCNN with ResNet50 and FPN, and DeepRAV v3 as reference models. See these blue lines here. We confirm from the ImageNet experimental results that the entropic student consistently performed best in terms of all the considered trade-offs, and supervised compression baselines outperformed input compression baselines with respect to XRD and three-way trade-offs. Similar trends can be found in object detection and semantic segmentation experiments. For the rest of the experiments, we put our focus on the image classification task for simplicity. Using ResNet50 as a reference model, we compare entropic student with the ResNet50 with including the entropy bottleneck introduced at its different layers: first, second, third, and fourth residual block, and average pooling of less than 50. As we previously pointed out and some of the recent studies reported, simply introducing bottlenecks at the late layers of the model can easily improve entropic students RD trade-off, as shown in the left figure. We also confirmed that such approaches are penalized by our new trade-offs, and as demonstrated in the middle and the right figure. We also compared codec-based feature compression methods at different layers with entropic student. The experiments show poor results of the codec-based feature compression compared to the supervised compression baseline. The last experiments are focused on entropic student because of its best performance confirmed in the previous experiments. While LesNet is a popular reference model in split computing studies, we explore other reference models for split compute for entropic student. Specifically, instead of LesNet 50, we used different reference models such as LesNet 101, LegNet Y, and hybrid VIT, Vision Transformer. The experimental results show that LegNet Y and hybrid VIT helped entropic students achieve the best trade-offs in this study. On top of these reference models, we also designed a more sophisticated encoder-decoder architecture inspired by mean-scale hyperplier model, shortly MSHP, for entropic student. Since the current entropic student uses factorized plier-based encoder-decoder. Note that the MSHP is a neural input compression model with a hyperplier, and FP, the factorized plier, does not contain any hyperplier. Our results show that the more sophisticated encoder-decoder improved RD trade-off at the cost of the large encoder size, which is emphasized in the middle and the right figures. Last but not least, we published a PyPy package named SC2 Bench. This is an MLOSS built on PyTorch for future SC2 studies. And you can install the package simply by pip install SC2 Bench. This package includes many supervised compression modules, and tools to support the SC2 studies. For instance, all the supervised compression models and the method used in this study are included as part of the package. We also published the code repository at this URL to help the community reproduce our results and benchmark new methods and models in the future. Okay, let us conclude the presentation by summarizing our work. In this work, we proposed a new benchmark in SC2, supervised compression for split computing. The benchmark involves two new trade-offs, which considers encoding cost on mobile devices as an additional metric. Using the proposed framework, we conducted a comprehensive benchmark study on SC2, involving 3 challenging computer vision tasks, 12 baseline methods, more than 180 trained models, various training methods, bottleneck placements, and model architectures. Overall, we conclude that the state-of-the-art supervised compression method at this time is entropic student because it consistently performed best in terms of all the 3 trade-offs considered in this study for the 3 computer vision tasks. Our code and the model weights are publicly available. We also released a PyPy package SC2 bench. We hope that our benchmark and the resources will help the future studies on SC2 in the community. Thank you for watching. Please check out our paper for more details.